My name is Rika, and this is my talk for RSS pioneers. My overall goal is to build transfer-aware representations that help seem to real, even if they're constructed from imprecise simulations. We'll first consider the problem of optimizing parametric controllers, where we will look for controller parameters x star that optimizes a given objective function f. And we will model the mean and uncertainty over f with a Gaussian process, where the covariance or the kernel function determines the influence, how far the influence of the already sampled points extends in the search space. The limitation of this setup is that most widely used kernels are stationary, meaning that they only consider distances between controller parameters. So we will learn kernel transforms from simulation to remove stationarity and to reduce exploration in undesirable regions. So first we'll simulate a large number of trajectories, and then we will learn lower dimensional or latent representations of this. One option is to train a neural network to output domain-specific summaries. For example, here for bipedal locomotion on atrias, we periodically record the center of mass, torso angle, and their velocities. In task-oriented grasping, we record grasp stability and task suitability scores and train a CNN to construct them. We also proposed a domain-agnostic option, a sequential variational autoencoder to embed the original trajectories into the space of latent paths and associate them with controller parameters. So with this, we can optimize controllers for the atria's biped. In this experiment, for example, needing fewer than 6 trials to find walking controllers in 5 out of 5 runs. For task-oriented grasping, we can significantly improve the success rate, and we can also show recovery from faulty or highly degraded kernels. With unsupervised approach to kernel construction, we can use the same code for different areas of robotics. For manipulation, for example, improving performance on the stable push task with Yumi, and we can learn to walk with the daisy hexapod here on the carpet, and also show that controllers that we find can perform reasonably well in a different environment here walking outside. Now, my long-term vision is to build priors from simulation without requiring a specific simulation scenario. We can employ topological data analysis for this to construct concise state representations to keep track of generic salient events such as formation and collapse of loops or formation or dissolution of connected components. We would aim to use the evolution of the topological state to infer state-dependent simulator sensitivity, meaning given a generic characterization of the scene as a sequence of topological features, we would aim to predict sensitivity of the simulation to noise or changes in control. And we can use such sensitivity priors to pick an optimal simulation step, for example, making the simulator execute at higher frequencies when anticipating salient events. We can also use the resulting estimate of this anticipated sensitivity or variance as a warm start for uncertainty estimation and explore further how such predictions can help reinforcement learning, for example, helping model-based learners to set an informed planning horizon. Okay, this concludes my talk. Thank you.